Welcome to today's Explainer. We're jumping right into the fundamental architecture of specialized computing systems, and we're doing it by unpacking a single, incredibly dense piece of source material. You know, it's honestly amazing how much vital information can be packed into just a handful of words if you know exactly how to read them. So today, we're taking a journey into the architecture of the machines that invisibly run our modern world, pulling apart the language used to actually design them. Let's get into it.
Section 1. The Blueprint of Computing.
We're taking this single, complex concept from our source, block diagram of computer with real-time application, and we are tearing it down to its studs to understand its true DNA. At first glance, sure, this just sounds like a dry, throwaway title you'd skim right past in an engineering textbook. But I promise you, by the end of our time together today, you're going to see this phrase for what it truly is. It's actually a thrilling, high-stakes roadmap for how machines are forced to interact with the unpredictable physical world.
Moving on to Section 2. Decoding the block diagram.
So, a block diagram basically maps out a system by representing its principal parts as blocks, connected by lines that reveal their critical relationships. What's really fascinating about this approach is how it lets systems engineers forcefully strip away all those chaotic, low-level details to create a totally clean, topological map of data and logic flow. Think about it. When an engineer builds an architecture, they absolutely don't start by mapping out individual copper lines or microscopic transistors. That level of granularity totally obscures the actual design. Instead, they isolate the function and the data path into distinct boxes. And this abstraction, it allows us to actually comprehend sprawling complexity by boiling it down to a series of interrelated logic states.
And that abstraction perfectly reveals the universal, underlying pipeline that literally any block diagram maps out. It fundamentally boils down to three unavoidable states: input, processing, and output. Whether we're analyzing a distributed edge computing network ingesting high-volume sensor telemetry or a high-frequency trading algorithm parsing market data, the core pipeline is identical. Unprocessed data enters from the external environment, a computational node evaluates and transforms that data, and an actionable result is transmitted back out. The blocks and lines just define exactly where and how that critical transformation takes place within the architecture.
Which brings us to Section 3, the core computer system.
Right, so a computer is formally defined as an electronic device for storing and processing data, typically in binary form, according to instructions given to it in a variable program. But in the context of systems engineering, this is the active compute node executing the logic of our entire setup. It isn't just a generic passive box. It's the very heart of the processing step we just established. It ingests the rigorous instruction sets we compile, applies them to incoming data streams, and executes them with relentless precision to drive the entire system forward.
Now, even without a literal schematic in front of us, architectural standards dictate that this central processing block has to contain specific subcomponents, and each of these represents potential bottlenecks and vital data pathways. We're talking about the implied architectural blocks managing the workload. You've got the central processing unit orchestrating the actual logic execution and clock cycles. You have memory dictating the bandwidth and latency for caching data arrays and instructions. And finally, the input-output interfaces, which govern the throughput connecting this internal digital logic to the messy external physical environment. Without these specific blocks perfectly tuned and communicating seamlessly, the whole architecture bottlenecks and the system just stalls.
Section 4. What is real-time?
Here is where things get really intense. Real-time designates the actual time during which a process or event occurs, requiring a system to respond to inputs virtually immediately, without delay. In real-time processing, computational speed transforms from just a nice-to-have convenience into an absolute non-negotiable architectural requirement. We aren't talking about some high-latency system where tasks can just wait around for hardware resources to free up. No way. We're talking about strict, unyielding, deterministic deadlines. In a real-time system, a late computation is fundamentally an incorrect computation. If the compute node misses its timing window by even a fraction of a millisecond, the logic collapses and the entire system fails.
To put that into perspective, standard computing allows for acceptable delays. Asynchronous tasks are put in a queue and handled whenever clock cycles become available. But real-time computing, it demands immediate processing with a strict zero-delay tolerance. Imagine if your car's anti-lock braking system used standard computing delays instead of reacting in real time. If you slam on the brakes on a sudden patch of black ice, you definitely do not want your car's computer putting that braking task in a background queue to process only after it finishes checking the tire pressure. You need a deterministic, zero-delay interrupt to pulse those brakes and literally keep you alive.
That life-or-death immediacy, that absolute guarantee of response time, is the true essence of a real-time application.
Now let's wrap this up in Section 5, the final application.
Returning to our raw source phrase, block diagram of computer with real-time application, we can now look at it with completely fresh eyes. We see it not as a simple title, but as a rigid blueprint for a highly responsive critical system. It isn't just a string of technical words anymore, is it? It is a highly specific, incredibly demanding recipe for a machine that must interact with reality on reality's schedule.
So when we synthesize all this, what do we get? A visual map of interconnected components built around a core processing engine at the center. This engine is bound by an immediate, zero-delay response constraint, and it's all directed toward a very specific, real-world task. This single phrase encapsulates an entire architectural philosophy where hardware capabilities, processing logic, and immediate physical action have to perfectly align. Every block drawn, every data path connecting them, and every single line of executable code must be optimized for absolute deterministic certainty and blistering speed.
And that brings us to a massive question. As real-time applications govern more and more of our world, from medical pacemakers keeping hearts beating, to autonomous drones navigating city skies, to the massive power grids keeping our lights on, how complex will the block diagrams of tomorrow need to be? I'll leave you with that provocative thought as you consider the incredible, invisible, zero-delay architecture running the modern world all around you. Thanks for joining me for today's Explainer, and keep looking for those intricate blueprints hidden in plain sight.